Welcome to the Millican Colloquium. Today we're very happy to have Sue Sierra. Sue Sierra is a professor and the personal chair of Noncommutative Algebra in the School of Mathematics at the University of Edinburgh, where she is also a member of the Hodge Institute. She received her PhD from the University of Michigan under J.T. Stafford, where she won the Horace H. Rackham Distinguished Dissertation Award. Sue then held an NSF Postdoctoral Research Fellowship. Her research is in noncommutative ring theory, algebraic geometry, and their interactions. Sue has been awarded 2 EPSRC grants.
That's British English for NSF. So.
Today she will tell us about enveloping algebras of infinite dimensional algebras. Please welcome Sue Sierra.
Great. Well, thanks very much for the invitation. So, particularly to Charlie for his hospitality. It's been a real pleasure to be here. This is actually my first visit to Texas. and changing planes in Dallas-Fort Worth Airport doesn't count. So I'm very much enjoying it so far. Let's see, I think the first thing I should do is explain my title. So part 0, is definitions. And the main question, and here are definitions. I mean, there's sort of two things I need to define in my title. So I'm first going to define infinite dimensional algebras, and then I have to tell you what I mean by enveloping algebras. So I'll start with infinite dimensional algebras, and here I'm going to define by example. So let's start with my second favorite, I can't quite decide, infinite dimensional algebra, which is called the Witt algebra. So what this is the ring of Laurent polynomials in a single variable t times the symbol del, which is always an abbreviation for d by dt. And I guess I should say here that everything I do is going to be over the complex numbers. So in other words, anytime I have a vector space, it's over the complex numbers. So I can get this from Laurent polynomials, because this is the vector space of derivations of the ring of Laurent polynomials. I am going to try to give this talk while defining as little as possible. So I'm going to try to define very little of the things I just wrote, but what I do want to say is, how is this an algebra? So, in an algebra, you're supposed to be able to take, algebra is, if you think about algebraic structures, you typically have ways to combine several things, right? In a group, you can multiply 2 elements. In a ring, you can multiply things or add them. So you need to have some operation here that will let me combine, say, 2 elements of this Witt algebra. So how do I combine 2 elements in here? So let's have a detour into some calculus. This is Calc 1. And trying to revise this. And suppose I've got 2 polynomials, and I want to take their derivative of their product. So okay, so I know what this is. gh prime plus h prime g. And now I want to think about, on both of these sides, how do I get this? How do I think about this element as something I get from h? So on this side, it's easy, right? I took h, I times it by g, and then I took the derivative. So I'm going to write this as del g acting on h, meaning I multiplied and then I took the derivative. So on this side, how do I get this from h?
It works better if you put your primes in the right place on the right.
It does, doesn't it? Yes. Let's.
You switched the order of H and G by accident, yeah?
I do have to do it. G prime H.
Yeah.
Thank you. Good. I'm glad that some people in the audience know calculus better than I do. Thanks, Sarah.
We can all solve what we wanted to see, though.
Good. So, okay, so how do I get this from H? Well, again, this one's easy. So I'm going to again write this as something acting on H. This one here, well, I took the derivative, and then I multiplied by G. And then this one here, I multiplied by G prime. So if I just put in boxes the things that are acting on H, then I must have equality between these two things that are now in red boxes, because as operators, say, on polynomials, they do the same thing. Okay, so how does this help me combine f del and g del? Well, this gives me an answer, right? What I should do is I should try to multiply them together using this rule, because I know what del g is. So this is f times g del plus g prime times h times del, sorry. In other words, that's fg del squared plus fg prime del. And we see we've got a problem, right? I'm trying to, if this is supposed to be an algebra, I should combine f del and g del, and I should be able to get something that's back in the bit algebra, right? And here I've got this del squared that totally messes me up. This thing is not in the bit algebra. But, so the problem is this fg term. But then I can use the useful fact that multiplication in the polynomial ring is commutative to get rid of fg. So, suppose I took this f del g del, which gave me something nasty, and then subtracted off their product in the other order. So then I got an fg del squared minus a gf del squared, so the del squared term is going to go away. And then the del term I'm going to have is an fg prime minus f prime g del. So now here, we've got an element of the bit algebra, and I'm happy here. So I'm going to define a binary operation, which is called a Lie bracket on W. So it takes an ordered pair of elements of W back to W, and the Lie bracket of f del and g del is fg prime minus f prime g times del. Okay, so good. So I've got now a sensible way to combine elements of my Lie algebra. So let's think about properties of the bracket. Well, it's antisymmetric, right? If I did these two in the other order, I would get -1 times this. It's linear, in fact bilinear, of complex numbers. I'm going to use my beautiful colored chalk to put up warning signs. It's a bit of a pain for anyone who likes algebra, because if you start figuring out what this does to triples of things, it's not associative, so it violates all of your intuition about how algebra should work. And this has various other properties that I won't write down. So in fact, if you get bored with the rest of this talk, you can figure out what other properties this particular Lie bracket has, and that will define for you a Lie algebra. So instead of talking more about the definition, this is what I'm going to do for the definition of a Lie algebra. Instead, I want to give some more examples. So I guess I need to, this is the board space I have, so I'll maybe try to use the top half of the board. So a second example. This is either my favorite or my second favorite Lie algebra, depending on my mood of the day. This is the Virasoro algebra, and as a vector space, so I'm to say equals some PSP to mean meeting as a vector space, it looks like Vit algebra together with a one more dimension. It's called a central. It's what's called a central extension of W. So what does a central extension here mean? Well, it means that this element Z is central. In other words, that I make Z and bracket with anything, I get 0. And then I just have to tell you, since the bracket's supposed to be bilinear, I just need to tell you what the bracket of two things that come from this piece that look like Vit is. And so I get the Vit bracket, Fg prime minus F prime G times del, plus some horrendous formula, which I'll write down. The residue at 0 of F prime G double prime minus F double prime G prime times it. So this is generally how central extensions work. You start with a Lie algebra. You have the bracket that you had before from the Lie algebra. Then you have this central element, and you change your bracket by adding on something times Z. And this horrendous formula, this is actually a cohomology theory, on which this is what's called a two cocycle. And two cocycles are a machine in Lie algebras to construct central extensions. So anytime I have a Lie algebra and a central extension, there's one of these two cocycles hanging around. Okay, so there's another example. Let me do a third example. So affine Lie algebras. So here, let's start. Let G be a finite-dimensional simple Lie algebra. So you will lose nothing if you just think that G is SL2, which is the set of 2 by 2 trace 0 matrices over C with the bracket being the commutator. And I think now I can get rid of the bit definition stuff. And then my affine Lie algebra, which I'll write G hat, is a central extension, so again as a vector space. I take Laurent polynomials now with coefficients in this finite-dimensional Lie algebra with an extra central element Z. And now again, Z is central, and then if I've got, say, an element, so an element of this piece is an element of my Lie algebra I started with times a Laurent polynomial. And here's another element y of my Lie algebra times the Laurent polynomial. I need to tell you how to bracket them together. And first of all, this piece alone is a Lie algebra. So this is called the loop algebra of G. And I need to, first of all, I'm going to tell you what the loop algebra piece of this bracket is. So I need a sensible way to combine these two elements. So there's really only one sensible thing you can do. You've got a way to combine x and y, because they're in a Lie algebra. You've got a way to combine f and g, namely multiply them together. So that's the bracket in loop algebra. And then there's some cocycle, which I'm not going to tell you. There's some kind of way of twisting this to get the z involved. Okay, so I've given you just a few examples, and this, you might say, well, what does this tell me about the entire, this is supposed to be a talk about developing algebras, infinite dimensional Lie algebras, and what I've given you is 3 examples of infinite dimensional Lie algebras. But in fact, these are reasonable examples to consider as pretty general examples, because Olivier Mathieu showed in a while back that L be an infinite dimensional Lie algebra, which is graded simple. It has no Lie ideals in a certain sense. And has polynomial growth, meaning it's not too big. We'll talk more about growth later in the talk. Then, in fact, there's only 3 families of these L's. L could be the bit algebra. L could be a more general algebra of derivations. So algebra of derivations on some polynomial ring. It could also be a subalgebra of this algebra of derivations. I'm not going to worry about defining those. Or a loop algebra for finite-dimensional simple Lie algebra. And again, this isn't true on the nose. There's a twisted version, but don't worry about that. So if you want to, so this is a reasonable group of Lie algebras to look at, and the point of this theorem is they're classified, and I've shown you what these ones will all look like. So the examples that I showed you are reasonably general.
So what happens if you take weight of several variables, it doesn't have polynomial growth anymore? Or?
This is hiding in
Simple.
what graded simple means. So let me just say it's hiding. It doesn't meet that criterion because I didn't want to get. Okay, so this is effectively telling you about part A of my title, but I'm 20 minutes into the talk and I better tell you about part B of the title. So let L be a Lie algebra with basis, xi for I in some index set. The universal enveloping algebra of L is U of L. So I'm going to write using a presentation by generators of relations. So first of all, I want to start with the free algebra. So this is non-commutative polynomials in my basis of my Lie algebra. And then I want some relations. My relations are that I want to force the commutator in this algebra to be the same as the Lie bracket for all elements in my basis. So this is associative, and it has the same representation theory as the Lie algebra. So of course I haven't told you what a representation of a Lie algebra is. In fact, you can take this as the definition. But I guess one way to think about this is if you're like me and you're a little bit alarmed by having this non-associative stuff kind of staring you in the face, then I could turn my horrible non-associative thing into a lovely associative ring that has the same modules and sort of acts on the same thing as the Lie algebra did. So if you're like me, you'd much rather think about this one than the Lie algebra. And the key the key basic fact about U of L is the Poincaré-Birkhoff-Witt theorem, which is universally abbreviated PDW, which is as a vector space, U of L looks exactly like a giant polynomial ring generated by the basis of my Lie algebra. So U of L is, if you like, a non-commutative deformation of this polynomial ring. And a fundamental fact about ring theory is that non-commutative rings are nicer than commutative rings. So I took this commutative ring and I made it nicer by making it non-commutative. And a corollary of that is if L is a finite-dimensional Lie algebra, then U of L has every good property in the world with because this polynomial ring does. And in particular, U of L has the property known as being noetherian from Emmy-Noether, i.e., since it's a non-commutative ring, I need to talk about not just ideals, but left or right ideals. And left or right ideals of the universally enveloping algebra are always finitely generated. So then the question, the basic question that motivates this talk and much of my research is, what can we say about the ring theory of U of L if L is infinite dimensional? And I guess I should say here that enveloping algebras of finite dimensional Lie algebras are some of the most well-studied non-commutative rings that are out there. A lot of the techniques of non-commutative ring theory were invented to understand them, but all of the understanding starts with the fact that there are deformations of these well-behaved and easy-to-understand commutative rings. Whereas for infinite dimensional Lie algebras, their enveloping algebras are much more mysterious. So in the rest of the talk, I want to tell you some stuff about the enveloping algebras of the Lie algebras I defined. So I started my talk with section 0, so that the number would help me keep track of what I was talking about. So let me talk first of all about one-sided ideals in developing algebra. So remember, non-commutative rings are nicer than commutative rings. So U of L is always nicer, or at least as nice as this polynomial ring. But on the other hand, this finite generation noetherian property, if I had an infinite dimensional Lie algebra, then I would have a polynomial ring in infinitely many variables. And then the ideal generated by all the variables would need all of those variables to generate it. So I would have a non-finitely generated ideal. So this argument does not work to say that enveloping algebras of infinite dimensional Lie algebras need to be noetherian. So 50 years ago, very nice to be talking about this now in 2024. Does there exist an infinite dimensional L with its universal enveloping algebra noetherian? And then, in fact, this was asked specifically about the Witt algebra in a paper in 1990. And people thought about it for a long time and were stuck. It was a hard question.
So the 1974 thing was just a question, not any kind of answer?
It was an answer for some particular, so for example, you can answer it easily if L is an abelian Lie algebra, so the Lie bracket is trivial, then here's the presentation. All right, if the Lie bracket is trivial, then this presentation just says the xy minus y, xi minus x, this commutator here is 0.
Right.
So in which case here the enveloping algebra is just the polynomial ring. So that's not noetherian. So there's and in fact it's also relatively easy to answer for the loop algebras and affine algebras. But for the Witt algebra for Virasoro, it's hard because that's a very non-commutative ring. Because a lot of almost all the lead brackets there are non-zero, which means it's very non-commutative, and therefore, since non-commutative rings are nicer, it's much nicer than the infinite polynomial ring, so it's got a really good chance of being noetherian. Right? But sadly, or happily maybe, the developing algebra, the bit algebra and Virasoro algebra are not noetherian. Actually, let me do this as a two-part theorem. Let me just say, rather than listing Mathieu's properties, let me say if L is the kind of Lie algebra that Mathieu classified, then its enveloping algebra is not noetherian. So as I said, this specific question had been out there for at least 23 years. And for a question that had been out there for so long, the proof is actually, it was staring mathematics in the face, which is the really surprising thing about the proof. So,
is that because people were hoping for the answer to be that other way?
No, I think people didn't know how to work with this algebra. I mean, so I'm going to define a homomorphism for you from the developing algebra of the bit algebra to a ring that I will write. Here I need my caution sign again. I'm writing this abusively as polynomials in T, T inverse, and del. And the caution here is because you need to remember this rule we worked out before. Del T is T del plus the derivative of T. So this is a famous and well-studied ring called the Weil algebra. And I should have called this map O for obvious. Right? So, well, this ring is generated by elements of Lie algebra, so to define a homomorphism, I just need to tell you where elements of Lie algebra goes. So, okay, I've got a polynomial times del. Where on earth should I send it? Why don't I send it to itself? Then the kernel of phi is not finally generated of either a left or right ideal. So of course, some work goes into proving this, but this is basically the proof. I mean, I guess I should say, why didn't anyone answer this? Because it turns out that the image of phi is a kind of ring that I talked a lot about in my thesis. And so then when I started thinking about this problem, I was like, wait a second, I know about the image of phi. Okay, so maybe it wasn't answered before because my thesis hadn't been written yet. I don't know. So let's move on now.
Is it finitely generated as a two-sided ring?
Aha! You have anticipated my...
Sorry.
And shake the hand of the man sitting next to you. So Charlie Conley and Christian Martin in 7. Not only is it finally generated, it's principled as a two-sided ideal. Right. So here, I start thinking. This is a picture I draw on the board to tell my students what you should be thinking or start writing the proof. So the thinking bubble says, whoa. Two-sided ideals and UOW are really big, right? I take one element, I make it into a two-sided ideal, and it's so big that it has all these infinitely many generators on the left and on the right as a one-sided ideal.
So because phi is the identity map up to some point, is the fact that the kernel you're saying the kernel is non-zero, is that because the T inverse part of the
No, the kernel is non-zero. No, the kernel is really big, right? So this looks like polynomials in infinitely many variables.
Mm-hmm.
This here looks like polynomials in two variables with some inverses, right? So this ring is huge. This ring is not.
Okay, so
there's a lot of stuff
it's
in the
not
kernel.
even an embedding, it's something
No,
interesting.
very, very non-inductive.
Okay.
So how do we say that an ideal is really big? Well, what I'm going to say is when I factor out the ideal, I get something small. So here I need to talk a bit about growth. So definition, let S be an associative ring, and I want it really to be a C algebra, so I want it to contain C so that everything is a vector space. S has polynomial growth if there exists a polynomial P of polynomial, say, with real coefficients, such that for all vector spaces contained in S, I should have said finite dimensional, the dimension, I can take my vector space and I can times together n elements from vector space, and I can measure how big the dimension of this power is. And I want the dimension to be bounded by P of n for n large. And if it doesn't have polynomial growth, it has just infinite growth. Oh, it has infinite growth. And then
So don't you need to like divide by dimension of v to the n or something?
no. So for example, in this ring, I can take my polynomial to be s cubed, or actually s to the 2 plus epsilon for any epsilon. Just any exponent bigger than 2. So, and now we get those things that are gonna let me say that ideals are big. S has just infinite growth if S has infinite growth, but anytime I've got a two-sided ideal of S, my notation for two-sided ideal is this normal subgroup symbol. I can say non-zero. Then S mod I has polynomial growth. out that this stinky thing turns into a theorem. So U of W has just infinite growth, and so does U of here once I quotient out by z minus lambda, where lambda is a scalar. So now I'm going to keep thinking. What I'm thinking is, okay, well, two-sided ideals in U of W, say, are really, really big, right? They're so big they all take this huge infinite dimensional, infinite growth algebra, cut it down to polynomial growth. So that maybe means that there aren't that many of them, because there's not room to have a complicated two-sided ideal structure. So U of W and U of here. Let me just say that all two-sided ideals are finitely generated. Right. So this is really hard. In fact, I'm not going to have any more theorems about Virasoro. I've run out of things I know about Virasoro. But I can tell you some theorems about loop algebras, about affine algebras, which kind of look like Virasoro, but they're actually easier to compute in. So I'm going to end by telling you some theorems for affine algebras, and then make some more conjectures for Virasoro. So this is a theorem I saw from Rackham Distinguished from a couple of years ago. So let G hat be an affine Lie algebra. Then, first of all, U of G hat factored by z minus lambda has just infinite growth for all scalars lambda. The second part, which is really a corollary of this, is very surprising. If lambda is non-zero, so now we were thinking, okay, wait a second. So if this has just infinite growth, then maybe this also has the property that two-sided ideals are finitely generated. And amazingly, a very much stronger version of this is true. If I take a non-zero z minus lambda and factor it out, then the enveloping algebra of G hat is actually simple. It has no non-trivial two-sided ideals. So I have two ideals in here. One of them is generated by 0, one of them is just 0, one of them is generated by 1 and is everything, and it's certainly both finitely generated. Sadly, I hope to talk about the proof, but I don't think I have time. So let me make this into a conjecture.
So this latter case, the not having a zero ideal, that's because G hat is going to be finitely generated as a Lie algebra? Or is that necessary?
So all of the algebras I'm talking about are finitely generated as Lie algebra, and the reason for that is because I'm interested in this noetherian property, and if the Lie algebra is infinitely generated as a Lie algebra, that immediately gets you a two-sided ideal that's infinitely generated. So you're gonna, like, if you're interested in noetherianity, you lose immediately. And I should say, the thing I didn't get to talk about is this really is a corollary. You need to know this before you get this, even though, of course, once you know this is simple, then of course it has just infinite growth, because if I have a non-trivial ideal, I factor it out and I kill everything. But you need that to get this. So I said that Virasoro looked like an affine algebra was more non-commutative, so it's more non-commutative, therefore it's nicer. So that strongly suggests that, again, non-trivial central quotients of U of Virasoro are also simple. So I want to end, though, with some bad news, or some more interesting news. I mean, I think the tension between this finite generation and failure of finite generation in these Lie algebras is really complicated and really interesting, and it's a lot of fun. So remember this first conjecture for Virasoro, or for U of W, which is that all two-sided ideals are finitely generated. And notice here, I'm assuming that lambda was non-zero. So Rackham and I proved this very early in 22. And so then we started thinking about what can we get for Virasoro. And of course we started thinking, okay, well, what can we say when lambda equals 0? And then that summer, my collaborator Alexei Patukov and I noticed that, I'm just going to do this with SL2. So the developing algebra of the loop algebra, which is the same thing as the developing algebra of affine SL2, factored by Z, has infinitely generated two-sided ideals. I mean, we already knew it wasn't one-sided Noetherian. I mean, that was in that theorem with Walton, and it's sort of the easy part, if you like, of that theorem with Walton. But this says this isn't even two-sided Noetherian. So, okay, so this simplicity result here, I said, was evidence for the simplicity conjecture for Virasoro. Is the failure of two-sided Noetherianity here evidence for the failure of this conjecture? Well, I don't think so. Again, my philosophy is that non-commutative rings are nicer than commutative rings, and the more non-commutative ring is, or the more non-abelian a Lie algebra is, the nicer its developing algebra is going to be. And this Lie algebra has a lot of elements that commute with each other if you go back to the formula for the Lie bracket in it and start playing around. Whereas here, almost nothing commutes with itself. So I think that this one is so much nicer, that is so much more non-commutative. This conjecture is still true, even though the analogous thing for the loop algebras is false. So let me stop here. It's a fascinating area with still lots of open questions. Thanks very much for having me.
Questions?
I'm still confused by this polynomial growth thing. So that the form n much bigger than 0, that can depend on V then?
Yeah, definitely. Yeah. So if I take,
I'm less confused that if
Okay.
that could depend on,
It definitely depends on B. So,
yeah, okay.
whoops. No, this is, so the polynomial doesn't depend on B, but the n depends on B.
Yeah.
Yeah. So, yeah.
Is it easy to give an example of a non-finitely generated two-sided ideal there?
Well, yes, but it's not going to help anyone to convince you that it's non-finitely generated. But again, it comes from an obvious homomorphism. So let's take, I always use phi, let's call this psi. So this is the preservation of parentheses homomorphism. Right, so here I take the Laurent polynomials in the Lie algebra and take the enveloping algebra of that. And here I take the enveloping algebra of SL2 and then adjoin a variable t and take the Laurent polynomials. But again, I said it's the obvious map. So here I've got an element of Lie algebra times the Laurent polynomial, and I take it to an element of the Lie algebra, which lives in here, and multiply it by these t's. And then here, actually, it's not the kernel, but the image of psi as infinitely generated two-sided ideals. But this is actually a good illustration of how you work with these big enveloping algebras. They're very, I mean, even this one, where it's much easier to compute it than the bit algebra, it's still kind of a pain. So what you want to do is map it to a smaller algebra which you control more easily, and then do computations there. So that was actually the way we, remember there was that kernel of this map phi from U of Vit to the Weil algebra, where the kernel was infinitely generated. What we did to prove that is we had another homomorphism to a different ring related to the Weil algebra, where you can get our hands on the image of the kernel of phi. And then the image of the kernel of phi wasn't finally generated. So therefore that meant the kernel of phi wasn't finally generated.
Is there an answer to that 1974 question?
Nope, I mean, yeah, it's very hard. Part of the issue is
So it's
that
possible there is no such thing.
I don't think there is such a thing, but I don't know how to prove it. I mean, part of the issue is that infinite dimensional Lie algebras are a real zoo. And Mathieu classified a bunch of them, but if they don't have this extra, if they don't have some kind of extra structure, then, I mean, it is true that any example that anyone has looked at far enough to be able to answer that question, the answer has been no, it's not noetherian.
So this other example in which you've mapped x times f to itself in some like strange way that crushes down your variables to just t and its inverse, can you give similar to Dr. Conley's question, can you give a brief description of how that really happens, going from so many variables to just really the one?
So SL2, so it's three-dimensional, and the standard basis for it is two triangular guys, which are conventionally called E and F, and then there's a diagonal traceless matrix called H, right? And then in this loop algebra, well, there's, for example, there's elements that look like E times t to the I. But on the other hand, in this loop algebra, or the enveloping algebra, there's no element t. So I usually, let's just write this as E sub I. And likewise, there's elements, say, F sub j and elements H sub k. Because when I write like this is a nice way to think about the elements of the Lie algebra, the enveloping algebra in math, because it makes you think there's a T you can multiply by, and there's not, right? But then, what's this homomorphism, psi? Well, for example, what's psi of EI? Well, it needs to go to something in here. So I don't have an EI in here, I just have an E. We'll send it to an E. And then, but I had a T to the I floating around. So let's send it to T to the I because I'm allowing myself to multiply by polynomials T. So it is the obvious now. Yeah. And it turns out that the image of psi has infinitely generated two-sided ideals.
Wow.
So.
Well, that just becomes more surprising. Okay. Fair enough.
Any more questions? If not, then let's thank Sue again.